Welcome to the deep dive. Today we're looking into something pretty amazing, silk. Now you might think, okay, silk scarves, maybe shirts, right? But what if I told you scientists are kind of turbocharging it, turning this natural fiber into materials that sound like pure science fiction? So a mission today is to really unpack how these new techniques, they're called crosslinking and plasticization, are completely changing the game for silk. We're talking about moving way beyond just strong threads to create these super versatile, adaptable materials, stuff with genuinely groundbreaking uses across all sorts of industries. Okay, so let's start unpacking this a bit. Silk, from silkworms, sometimes spiders, it's naturally one of the strongest things out there in nature. We've used it for ages in textiles, obviously, and more recently things like medical stitches. But a key thing is it's also renewable, it's recyclable, sustainable, pretty eco-friendly stuff.
Exactly. And what's really fascinating is how researchers first began to see its potential beyond just, weaving it. They figured out how to reverse engineer the core protein. It's called silk fibroin from the cocoons. Basically dissolve it down into a liquid. And that allowed them to process it into totally new forms, things, films, fibers, sponge-like scaffolds, even 3D printed shapes. Initially, the stability of these new materials mostly came from silk's natural internal structure, these things called beta sheets that act like tiny physical crosslinks, little anchors holding it together.
Right, so that was a huge leap. But those early engineered silk, they weren't perfect, were they? I remember reading they were often kind of cloudy, maybe a bit brittle, and they degraded slowly, which isn't always ideal. And sometimes integrating them with living cells for more advanced biotech stuff was tricky.
That really brings us to the key question, doesn't it? How do we get past those limitations? How do we make silk genuinely elastic, super flexible? And how do we make it work smoothly with really modern manufacturing, like photolithography, using light for super precise patterns and the latest 3D printing techniques? Well, the answer, and what we're diving into now, lies in these new ways to stabilize and tweak the silk, specifically covalent cross-linking and plasticization. And these aren't just small adjustments, they're really kicking off a whole new era for silk materials, massively expanding what's possible, even for just general use.
Okay, this is where it starts to sound really cutting edge, covalent cross-linking. So instead of just relying on those natural anchors you mentioned, this is about creating actual strong chemical bonds within the silk itself.
That's precisely it. Strong, stable chemical links. And there are two main ways we're seeing this done: dityrosine cross-linking and methacrylate modification. Let's start with the first one.
The tyrosine.
Okay, right. So dityrosine cross-linking is, well, it's a pretty neat natural approach. It uses specific amino acids called tyrosine residues. And the key thing is these are already part of the silk protein chain. So you don't need to chemically mess with the silk beforehand. And when you encourage these natural residues to link up, the silk materials become optically clear, totally transparent, and remarkably elastomeric.
Elastomeric, meaning stretchy, like really stretchy.
Exactly. They can stretch a lot and then bounce right back to their original shape, which, as you can imagine, makes them fantastic for biofabrication, like building scaffolds to grow new tissues, or even encapsulating living cells right inside the material.
Wow. Okay, so how do they actually trigger these tyrosine links? What's the mechanism?
Well, there are a few clever strategies they've developed. One uses enzymes, something like horseradish peroxidase, HRP, with a bit of hydrogen peroxide. Now, the basic chemistry was known way back, like the 1960s, but people didn't really grasp its potential for making these advanced materials until around 2014. That's when they showed you could make these transparent, super elastic, and really fatigue-resistant hydrogels water-swollen networks. And some surprising applications came out of that, like biodegradable green LEDs. The lenses made from this silk, if you coat them with a bit of paraffin wax, can apparently last for about 3 years. It's a great eco-friendly option compared to plastics.
Biodegradable LEDs, that's brilliant for cutting down electronic waste. But you mentioned enzymes.
Mm.
Are there any downsides, any hurdles with that approach?
That's a really good point. Yeah, sometimes the enzymatic reactions can be a bit on the slow side. And if you were to implant these materials, there's a small chance the enzymes themselves could trigger an immune response. But researchers are definitely working on that. They're developing ways to stick the enzymes onto tiny particles so they stay put, or exploring alternative enzymes that the body is less likely to react to.
Okay, makes sense. What other ways are there besides enzymes?
Another method is the Fenton reaction. This one's much faster, can form gels in 30 seconds flat. Early versions tended to be a bit opaque, a bit cloudy, but newer work using special iron chelating particles has resulted in clearer gels that are also, interestingly, highly adhesive.
Adhesive, like a biological glue.
Sort of, yeah. Imagine a biocompatible glue that could quickly stick to and seal tissues. That's the potential there.
Okay, fast and sticky. What else?
Then you've got photo-initiated methods, using light. And the big plus here is control. You get really precise spatial and temporal control. You can basically cure the silk exactly where you shine the light and exactly when. One system uses ruthenium and something called SPS. It gels super fast, less than a minute, into clear gels. And what's really critical here is that you can pack these gels with a lot of cells. Think about engineering human cartilage, for example. And unlike some other cross-link silks we'll talk about, these ones don't tend to spontaneously stiffen up over time, which is much better for keeping the cells happy and viable long-term. It's even shown promise as a tissue sealant in studies, like successfully sealing up lung wounds.
Wow, that sounds incredibly useful, especially the not stiffening part. Any other light-activated methods?
Definitely. Another really neat photoinitiator is riboflavin, which is just vitamin B2. It's naturally in our body, so it's extremely biocompatible, very cell-friendly. This has led to some cool applications, like materials that can stick directly onto the cornea for eye repair, or even 3D printing tiny silk microneedles. They're strong enough to painlessly go through the skin barrier to deliver drugs or vaccines. Imagine that painless injections.
Microneedles made of silk. Okay, these applications are getting wilder. You mentioned some silks stiffen over time, though. These transparent, flexible ones sound great, but does that happen to them too?
Yeah, that's an important aspect to consider if we step back a bit. Yes, some of these covalently cross-linked hydrogels, especially the ones made using enzymes, can undergo a spontaneous change. Over time, they can rearrange themselves into that stiffer, more opaque structure rich in beta sheets. Now, for some uses, that's obviously a limitation if you need consistent flexibility. But you can actually use that property. For example, researchers found that this stiffening process can actually trigger programmed cell death apoptosis in cancer cells trapped inside the gel.
Whoa, wait, so the stiffening kills cancer cells?
In some experiments, yes. It makes these materials potentially interesting for targeted cancer therapies or research models. It's about turning a potential bug into a feature.
That's really clever. Okay, so you have these different dityrosine methods. Can they mix and match them, combine techniques?
Absolutely. Combining, say, the dityrosine cross-linking with some controlled induction of those stiffer beta sheet structures allows for really fine-tuning the final properties. You can get materials that are both incredibly tough and flexible, often better than what you'd get with either method alone. They've used this combined approach to stabilize enzymes, for instance, like an enzyme called carbonic anhydrase, which captures CO2. Embedded in this tuned silk, it kept almost all its activity after being used 6 times. It really lets you engineer complex, hierarchical materials that mimic structures found in nature. There was this amazing example of a web-shaped silk hydrogel designed to hold over 4,000 times its own weight.
4,000 times. Okay, that's some serious strength. It really does sound like designing materials atom by atom almost.
Which is a perfect segue into the second main type of covalent cross-linking. Methacrylate modification. This is what you might call the truly engineered approach. Here, scientists chemically alter the silk protein itself, attaching these special light-reactive groups called methacrylates. Now, unlike the dityrosine method, this does require modifying the silk chemically first. But the payoff is incredible precision. It gives you really fine control for engineering features at the nano and microscale. Think tiny, tiny patterns made very accurately and quickly, often without needing any molds.
Okay, so if dityrosine gave us transparency and stretchiness, what kind of mind-blowing things does this methacrylate precision enable?
Well, early on, they used it to create things like biodegradable optical components like tiny ellipses or iridescent patterns, but more recently, it's enabling things like flexible bioelectronics. Imagine ultra-thin glucose sensors that are so sensitive, so thin, they feel like a temporary tattoo, and they harmlessly dissolve in the body after use. Perfect for skin-like electronic interfaces.
Like smart skin.
Pretty much. And another really cool example is silk kirigami. the Japanese art of paper cutting, they apply that idea to these UV cross-linked methacrylate silk sheets. They make precise cuts, and these sheets can then stretch, bend, twist, and conform perfectly to weird shapes, like your skin, while maintaining their electrical conductivity. No need for sticky adhesives.
Wow, Kirigami electronics. That's
Yeah.
creative. Is this area still evolving? Newer methods for this modification?
Oh, definitely. There's a newer modification using something called glycidyl methacrylate, or GMA. A key advantage is that it allows processing in just water, making it even more biocompatible. And this has unlocked some really impressive stuff, like using DLP digital light processing, a type of 3D printing to create silk hydrogels with just astonishing mechanical strength. Seriously, they showed one supporting a 7-kilogram kettlebell that's over 15 pounds, and then bouncing right back to its original shape.
A 15-pound kettlebell, supported by a silk hydrogel.
Yep. Which immediately suggests potential for really robust medical implants, maybe replacing things like heart valve leaflets, arteries, or other tissues that need to be strong and flexible. They're also using extrusion-based 3D printing with this GMA silk to build scaffolds that help guide the formation of specific tissues like cartilage inside the body. And another big one, in situ tissue sealants. For minimally invasive surgery like laparoscopic procedures, this modified silk shows excellent hemostatic properties. It stops bleeding fast and adheres really well to wet tissues like the liver or stomach right during surgery, helping things heal.
Okay, we've covered strength, precision, transparency,
Mm.
but you also mentioned flexibility at the start. How do they make silk super soft and pliable? That seems like the opposite of strong.
Right. That brings us to the other major strategy, plasticization. This is all about creating soft, flexible silk materials. Think bioplastics, or materials for advanced bioelectronics, where softness and stretchiness are key. One really common way is glycerol plasticization. Glycerol is, a simple, safe compound. Adding it to silk increases the mobility of the protein chains. It basically makes the silk molecules slide past each other more easily, resulting in materials that are soft and flexible even when they're dry. People are looking at this as a sustainable alternative to petroleum-based plastics, maybe for food packaging or medical applications. And a really standout use is in adhesive, flexible electrodes for ECGs, measuring heart activity on the skin. These glycerol plasticized silk electrodes actually showed better signal quality than standard commercial gel electrodes.
Better than the standard hospital ones, even when moving or sweating.
Exactly, even during sweating or under significant stretch, which is a huge deal for reliable, wearable health monitoring.
Okay, so glycerol adds flexibility. You mentioned another way.
Yes, calcium ion plasticization. Calcium ions are fascinating here. They play really complex roles. They help dissolve silk into even tinier structures called nanofibrils, and they stop the silk from becoming too crystalline and brittle when it dries. The result is silk materials that are unbelievably stretchable. We're talking rupture strains, how much they can stretch before breaking up to 1,300%. That's just incredibly high for silk.
1,300%. That's hard to even picture. What do you do with silk that's stretchy?
All sorts of things. Biodegradable temporary batteries, for one. Optical strain gauges that can wrap around a joint and measure huge ranges of motion in real time. Wearable electrodes for healthcare, again. And what's really interesting with the calcium is that it can make the silk act like a reusable adhesive. So electrodes made with it stick reliably to the skin without causing irritation like some glues, giving stable measurements even if you're exercising.
Reusable sticky electrodes. That'd be convenient.
It really would. And it's enabled the development of things called e-tattoos. These are ultra-thin electronic patches, almost invisible on the skin. They're conductive, they can sense strain, humidity, temperature. And get this, they are self-healing. If they get scratched or torn, they can mend themselves almost instantly, like 100% healing efficiency in just 0.3 seconds.
Self-healing electronic tattoos. Okay, now you're just showing off.
Chuckles slightly. It does sound like science fiction, doesn't it? But it's real research. And related to that is something called Caregum. This is a 3D printable kind of gummy material that incorporates this calcium plasticized silk. It has incredible toughness, that insane elongation, up to 25,000% in some cases, and it self-seals in seconds if cut.
25,000%.
Yeah, it's almost liquid-like in its stretchiness but holds together. They're thinking about it for bionics, human-machine interfaces, soft robotics, things that need to be incredibly tough but also compliant and self-repairing. It can even act as a transfer stamp in making electronics, changing its stiffness with humidity to gently pick up delicate microcomponents and place them onto curved surfaces like skin.
It covers such a massive range, from super rigid, precise structures made with light, all the way to this incredibly soft, stretchy, self-healing gum, all from silk.
It really does span the spectrum. And, while there are a few other chemical methods people have tried for cross-linking, like using glutaraldehyde, they tend to be less suitable for working directly with cells or using inside the body because of toxicity concerns. So the methods we've talked about, the dityrosine cross-linking, the methacrylate modification, and these plasticization techniques, they really represent the most impactful and broadly applicable ways researchers are unlocking silk's potential today.
So wrapping this up, what's the big picture here for you, our listener? We've seen how silk, this ancient material, is being fundamentally transformed. Scientists aren't just using it, they're engineering it to have properties we never thought possible, making it transparent, super tough, incredibly flexible, even self-healing and adhesive.
Right. And these innovations mean silk can now be used with the most advanced manufacturing techniques, sophisticated 3D printing, light-based patterning. It's opening up this huge range of possibilities. We're talking next generation medical implants, really smart wearable sensors that feel like skin, sustainable bioplastics to replace conventional ones, and even the building blocks for future bioelectronics.
It really positions silk as a material for the future, doesn't it? A sustainable blueprint derived from nature that could help us create all sorts of new polymer technologies to meet our needs, from healthcare right through to electronics.
It absolutely does. But, this also raises a really important question as we look ahead. As these amazing silk-based products start moving from the research lab towards actual commercial products, how do we handle the natural variations? Silk from different batches of cocoons can be slightly different. How will manufacturers ensure consistent, high-performance materials every single time, especially for really demanding applications like medical implants? What new engineering solutions or quality control methods will be needed as we keep pushing the boundaries of what this incredible natural polymer can do?
That's definitely something to think about the next time you see or touch something made of silk. Thanks for joining us on this deep dive.